Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Postgraduate Diploma in Analytical Chemistry, PGDAC. MCH002 Separation Methods. Block-1 Classical Methods. Unit-1 General Aspects of Separation Methods, 1.1 Introduction. The world around us consists of an innumerable complex materials, organic, inorganic, and those containing both types. In order to know the impact of their existence on our life and fruitfully recover useful materials from various natural resources, we have to know their composition and develop chemistry for their recovery. We may like to look at another scenario where the human population of today has become very much demanding in terms of purity of materials, better products, and security, particularly in terms of health. Simultaneously, science has tremendously grown in its dimensions and the need for ultra-pure materials is fast increasing. You will, thus, realize that the entire scenario requires developments in the methods of analysis, including separations. It is pertinent to point out here that separations are not only important for analysis but assume great significance in the synthesis and recovery of pure materials. Separations touch every branch of science and technology and have developed into a well-established branch known as separation science. If you just look at the developments, say in biological sciences, such as biochemistry, biotechnology, clinical pharmacology, therapeutics, and toxicology, the progress has taken place prominently because of the advancements in the separation methods. After going through the preceding text, you would realize that separation methods form an important component of chemistry and particularly analytical chemistry. This course on separation methods is designed to include theoretical aspects, instrumentation, applications, advantages, and limitations of some of the important methods of separations. Before you study the individual separation methods, it may be necessary to get an overview of the separation science. This particular unit deals with the concept of separations as a unified science, scope of separations highlighting their utility, classification of separation methods, and the criteria for the selection of separation methods. Objectives. After studying this unit, you should be able to appreciate the separation methods as a unified science, describe the scope and utility of separation methods, discuss the evolution of chromatography, explain the classification of separation methods, and list the criteria for the selection of separation methods. 1.2 Separation methods minus a unified science. The separations play a key role in the various branches of science and technology, but they themselves form a unified branch of science. The subject of separation science essentially deals with the physical and chemical phenomena involved in achieving the separations. The outcome of separations is very much dependent upon the physiochemical principles resulting into separations. It also involves the development, application, and reproducibility of various separation processes. The separations have assumed such a paramount importance that a common man has become familiar with the meaning of word separation. However, with its requirement and usage, the definition of separation has become a little complex. In the simplest terms, separation is defined as an operation in which a mixture is divided into at least two components having different compositions. But this particular definition has a limitation as it does not cover chiral separations in which molecules of same composition and chemical structure are involved. The molecules differ only in their stereochemistry. Therefore, a broader definition of separation will be as under. Separation is a process by which a mixture is divided in at least two components with different compositions are two types of molecules with the same composition but different stereochemistry. After having learned the definition of separation in true chemical sense, you should be clear about the different objectives for achieving separations. I. Analysis of different constituents of a mixture. E. Procuring pure materials from complex mixtures. In analysis, referred above in I, there may be three aspects. Removal of interfering constituents before the actual quantitation of one or more known compounds. Isolation of unknown constituents for subsequent characterization. Analysis of a complex unknown mixture by subjecting the entire sample to separation into individual constituents. Under E, for obtaining the pure materials from complex mixtures, the constituent with the desired purity may be obtained by applying a single process or using a number of separation techniques. In some cases, in order to attain the required level of purity, the separation steps of the same process may have to be repeated. The mixtures to be separated vary largely in terms of their complexity. They may contain constituents which differ in their molecular weights, solubility in a solvent, volatility or other properties. The sizes of species may range from atomic dimensions through organic molecules and macromolecules to molecular aggregates. A large number of separation methods are available that utilize selected characteristics as means of separation. Each of these methods can be further subdivided into different techniques using unique characteristics. In certain cases, the properties of the constituents may be so different that very simple techniques of separation can be applied. A very simple example, in this regard, is the recovery of common salt from seawater. However, in other cases, the properties of constituents may be so similar that the separation becomes a tedious job. A very well-known example of a difficult separation is the separation of zinc, IV, and HF, IV. The other example in this category is the separation of optical isomers. Another important parameter which is critical in choosing the separation is the amount of mixture available. In some cases, the amount may be a few molecules. However, in industrial processes it may run in tons. 1.3 Scope of separation methods. We have learned that the separation science deals with a variety of problems at hand. Now, it may be necessary to illustrate the utility of separations by citing example from daily life to various branches of science and technology. The number of even the important examples is so large that they cannot be recounted here. However, by citing a few, you will be able to appreciate the significance of separations. The art of separations is not new to the present-day community of scientists. Even our ancestors were familiar with the various separation methods and were using them for their daily needs. A very typical example is the distillation of alcohol for drinking in other purposes. Isolation of various dyes for coloring purposes from natural materials is a good testimony of their skill for achieving separations. They were also quite proficient in isolating metals for their use from ores by applying different separation procedures. A number of drugs used to be isolated from plants and herbs. The treatment of waters by solid adsorbents is as old as the civilization. There are records available that in the time of Aristotle, sand filters were used for the purification of sea water and impure drinking water. Moses used tree branches to make bitter water sweet. Separation processes play a key role in our daily life. We remove undesirable gases and particles from the air we breathe. The municipal drinking water undergoes several purification steps. It is well known that the identification and removal of contaminants from food are largely possible due to separation processes. One of best examples of use of separations in industry is the availability of a variety of products from crude petroleum. The nuclear age did really take off due to improvements in the methods of separation of U-238 and U-235. The requirement of high purity materials in industry, particularly for semiconductor, is met due to advancements in separation processes. It has been possible to understand the different biochemical processes taking place in our body due to advancements in separation processes. The separation processes have given a unique gift in the form of artificial kidney. The success in the studies on human genome and proteomics owes a great deal to advancements in separation sciences. The synthesis of different medicines is possible due to efficiency of separation processes. The identification of explosives has been possible due to a key role of separations. In a nutshell, there is hardly any walk of life where separations do not play their dominant role. It is well known that a large number of separation methods fall under the category of chromatography, and that is why the separation methods have become synonymous with chromatography. Thus, before proposing a classification of separation methods, it may be important to give here a brief description of evolution of chromatography. 1.4 Evolution of chromatography. There is a large number of separation methods which vary in their utility in a particular situation. Many of these important methods fall under the category of chromatography. Therefore, before we discuss classification of separation methods, it will be appropriate to give an idea of the chromatographic science. In Unit 4 of this course, a discussion on classification and general principles of chromatography has been presented. Following this unit, some of the units discuss important chromatographic methods in detail. In order to keep the text of this particular unit properly jointed, a brief idea about the evolution of chromatography is being presented here. The subject of chromatography had a very modest beginning. The principles and applications were reported in 1906 by a Russian botanist, Mikhail Svet. He described the resolution of chlorophylls and other plant pigments in a plant extract. A petroleum ether solution of chlorophyll was passed through a calcium carbonate column. By passing the solvent through the column, the pigments were resolved into various zones. This separation became practical if after the pigment solution, the pure solvent was allowed to pass through the column. Such a preparation was termed as the chromatogram, and the corresponding method, the chromatographic method. The term chromatography is derived from the Greek words chroma and graphy, meaning color writing. The discovery of chromatography was made with the separation of colored compounds, but its potential for colorless compounds was realized. Svet himself anticipated the potential of this technique for a wide variety of compounds. This technique is now termed as liquid-solid adsorption chromatography. Following the discovery of original form of chromatography, several new advances were made in the form of ion exchange chromatography, partition chromatography, and gas chromatography. The logic of naming Svet method as chromatography does not hold good today because most of the compounds separated by this technique are not colored. The name is very well established and is not likely to change. Not only this, many other techniques leading to the redistribution of components of a mixture are included under the head chromatography. The most important advances in chromatography were introduced by James N. Martin. The impact of chromatography has been very great on all the areas of analysis and on the general progress of science. Recognition of this fact resulted in the award of Nobel Prize in 1952 to Martin and Sons for their pioneering work in this field. As has already been mentioned, we see chromatography in its different forms. A general definition of chromatography covering its various forms is as given under. Chromatography is a method of separation in which the components to be separated are distributed between two phases. One of these is called the stationary phase and the other the mobile phase, which moves on the stationary phase in a definite direction. The stationary phase may be a solid or liquid, and the moving phase may be liquid, gas, or supercritical fluid. The components of a mixture redistribute themselves between two phases mainly by the process which may be adsorption, partition, ion exchange, or size exclusion. For the purpose of simplification, in our discussion here on the classification of separation methods, we will not include supercritical fluid as one of the mobile phases. However, this will be taken up later. 1.5 Classification of separation methods. The subject of separation science has grown very large in its dimensions. A variety of methods have come up on the forefront to meet the different needs. A number of well-known techniques have undergone modifications. The growth in the number of separation methods can be attributed to the following factors: different separation goals, diversity of mixtures to be separated, and utilization of a variety of physiochemical phenomena for separations. The separation methods are generally named after the forces or phenomena that give rise to separation. In this respect, we can cite the examples of precipitation, crystallization, extraction, adsorption, and ion exchange. At times, the name is used to reflect upon a distinct form of operation. Here, you can mention techniques like filtration, distillation, and chromatography. Chromatography, for example, can employ any number of forces such as adsorption, partition, ion exchange, and size exclusion. The above discussion makes it clear that one of the classifications of the separation methods may be based on the property which results into separations. The other approach that can be adopted for classification is based on the physiochemical phenomena responsible for separation. To simplify, we can further divide these phenomena in two major categories, equilibrium processes and rate processes. Thus, we can propose two types of classifications for separation methods. Based on the property resulting into separation. Based on the equilibrium and rate processes. It may be pertinent to point out that the details of the methods will not be discussed here because either some of the methods are well known or a few of them are being discussed in details in other units of this course. 1.6 Classification based on property resulting in separation. The main properties which result into segregation of components of the mixture are volatility, solubility, partition, ion exchange, surface activity, molecular geometry, and electromigration. 1.6.1 Volatility. The methods based on volatility mainly include vaporization and distillation in its different forms. Sublimation is a special case of distillation where a solid is directly vaporized without passing through a liquid state. Vaporization is simple where solvent is removed by using heat or air currents such that the material concentrates to a solid. In separation by distillation, all the components of interest in the mixture are volatile. Sublimation is an exception to this because of the physical state of the component. Distillation depends on the distribution of constituents between the liquid mixture and the vapor in equilibrium with the mixture. The more volatile component is concentrated in the vapor while the less volatile components remain in the liquid phase in greater concentration. There are various forms of distillation such as fractional distillation, flash distillation, vacuum distillation, steam distillation and azeotropic distillation. Fractional distillation involves the return of condensate to the distillation unit under conditions such that this condensate is continuously and counter-currently in contact with the vapors. By this method, you can achieve greater enrichment of vapors of more volatile component than that obtained by simple distillation. In flash distillation, there is an instantaneous and continuous vaporization of a definite component of the mixture such that the total vapor produced is in equilibrium with the remaining liquid. Vacuum distillation is actually distillation under reduced pressure. It is used to separate high boiling mixtures or liquids that decompose below their normal boiling points. Low pressure reduces the boiling point. Steam distillation is employed to separate a component from a non-volatile impurity. The boiling temperature of the mixture is reduced by vaporizing it in a stream of carrier vapor, say steam, which upon condensation is immiscible with the original mixture, and thus, a separation can be readily achieved. Azeotropic distillation is used for separating components of a mixture which boil very close to each other. The relative volatility of the components of the mixture is altered by adding another substance. This description will give you an idea about the different ways the distillation can be carried out for different types of mixtures. 1.6.2 Solubility. When we refer solubility as a means of separation, it essentially implies precipitating the constituent of interest from the solution. When the solubility limit of the solute in the solvent exceeds, the material appears as a precipitate. If this process is carried out in an appropriately selected solvent and in a controlled manner, it can lead to crystallization. Precipitation can be brought about in a number of ways, out of which some important ones are discussed below. Solvent precipitation is achieved by adding another miscible solvent to the solution, such that the solubility of the component of interest is reduced and the material appears as a precipitate in the mixed solvent. The precipitation brought about by a chemical reaction is well known. Right from the beginning in a chemistry laboratory, you have been precipitating different ions by adding appropriate reagents. A typical example is precipitating bar-2 by adding SO4. 2. There are many selective reagents known which can precipitate one ion in the presence of other ions. A detailed discussion about this is given in Units 14 and 15 of the course on Basic Analytical Chemistry. However, some organic compounds can be precipitated by suitable adjustment of pH. It is possible to precipitate weakly basic organic compound from an aqueous solution by making the solution more basic. Similarly, organic acids can be precipitated by making the solution more acidic by strong acids. 1.6.3 Partition. The methods based on partition require two phases and there has to be a redistribution of components between these two phases. Some important types of methods fall under this category, and they are as follows: liquid-liquid extraction, liquid-liquid partition chromatography, gas-liquid chromatography. Liquid-liquid extraction is popularly known as solvent extraction. When a solute is brought in contact with two immiscible solvents, one of which is invariably water and the other organic, then it distributes itself in them in a fixed ratio. In certain favorable conditions, the solute of interest can be more or less completely transferred from one phase to another. This purification technique finds applications in separation, purification and enrichment. This separation method has been discussed in detail in Units 2 and 3 of this course. In liquid-liquid partition chromatography, there is a support which holds the stationary liquid phase and a mobile liquid phase runs over it. Because of the requirement that the two liquids be immiscible, it follows that they differ markedly in polarity. Either the more polar or less polar may be immobilized. Most commonly, a polar solvent is held on the support. If a non-polar solvent is held after making the support hydrophobic, this is called reversed phase chromatography. The components of the mixture redistribute themselves in the two liquid phases, resulting into separation. It is in some ways similar to liquid-liquid extraction discussed above. If the support material is packed in a column, the method is known as column liquid-liquid partition chromatography. The details of this method are discussed in Unit 5 of this course. A simpler version of this technique is available in the form of planar or two-dimensional chromatography. The support is either a thin layer of inert material coated over a glass plate or a chromatographic paper. And hence, we have two types of two-dimensional chromatography: thin layer chromatography and paper chromatography. In these two cases, the mobile phase can be made to move either from top to bottom or bottom to top, and thus, there are two modes of operations: descending and ascending chromatography. The details of planar chromatography are discussed in Unit 6 of this course. An improved version of liquid chromatography is in the form of high-performance high-pressure liquid chromatography, HPLC. It is one of the most widely used separation techniques. The particle size of the packing material is much smaller, and a high pressure around 6000 psi is applied at the top of the column. A high-pressure version of thin layer, HPTLC, is also available. Unit 8 of this course incorporates the details of this technique. In gas-liquid chromatography, the stationary phase is a liquid coated in a column or on a support packed in the column. The mobile phase is a carrier gas which carries with it the sample in form of a gas. The sample is volatilized to be carried through. The partitioning takes place between the carrier gas and the coated liquid. The different aspects of this separation technique are elaborated in Unit 7. 1.6.4 Ion exchange. In ion exchange, there is an exchange of ions, cations or anions between an insoluble solid material and the solution in contact with it. The solid material, called ion exchanger, carries exchangeable cations and anions. When the exchanger is in contact with an electrolyte, these ions can be exchanged for a stoichiometrically equivalent amount of other ions of same charge. Carriers of exchangeable cations are known as cation exchanges and carriers of exchangeable anions as anion exchanges. Certain materials are capable of both cation and anion exchange and are known as amphoteric exchanges. Generally, ion exchange is performed in columns. However, in some cases, batch operations are carried out. A very special case of ion exchanges is chelating resins. These resins contain functional groups which are chelating ligands. They form multiple bonds with complex forming metal ions. These resins have much higher affinities for transition metal ions than for alkali metal ions. 1.6.5 Surface activity. In surface activity, it is the property of adsorption which is mainly used for separation. The methods can be chromatographic and non-chromatographic. The chromatographic methods are as follows: liquid-solid adsorption chromatography, gas-solid adsorption chromatography. In liquid-solid adsorption chromatography, an active adsorbent acts as a stationary phase and the liquid as a mobile phase. The stationary phase can be in the form of a column or a thin layer on a glass plate. Paper chromatography cannot be exclusively classified as liquid-liquid partition chromatography. If the cellulose of the paper is playing an active role as an adsorbent, it will be justified to put it under the head of adsorption chromatography. The high-pressure, high-performance versions of adsorption chromatography both on column and thin layer are in use. In gas-solid adsorption chromatography, the carrier gas with the volatile components of the mixture flows over an active adsorbent packed inside the column. Because of differences in adsorption affinity of the components, the segregation of the components takes place, as compared to gas-liquid chromatography in which a liquid is coated over an inert material packed inside the column. Here in gas-solid chromatography, an adsorbent is packed. The details of the two types of adsorption chromatography and the high-performance version of liquid-solid chromatography are discussed in the respective Units 5 and 6 of Block 2 and Units 7 and 8 of Block 3 of this course. An ultimate extension of adsorption chromatography is affinity chromatography. It is relatively a new advancement and is an important tool for biomedical research. The technique of affinity chromatography exploits the unique biological specificity of a ligand-macromolecule interaction. The concept of affinity chromatography is realized by covalently attaching the ligand to an insoluble support through an spacer arm and packing the material into a chromatographic bed. If a mixture of several proteins is passed through the column, only that protein that displays appreciable affinity for the ligand will be retained or retarded. The others which show no recognition of the ligand will pass unretarded. The adsorbed protein can be subsequently eluted by changing the composition of the solvent to permit dissociation from the ligand. The potential of this technique for the purification and isolation of biological molecules is unlimited. Specific adsorbents can be designed for the purification of enzymes, antibiotics, nucleic acids and proteins. 1.6.6 Molecular geometry. There are a number of methods based on molecular geometry. They require a permeable barrier to provide separation. The methods are based on the following: molecular sieves, gel filtration. The permeable barrier separation process of practical importance utilizes semi-permeable membranes as the restrictive surface. The membranes permit the passage of certain chemical species completely while preventing or strongly retarding the permeation of others. It may be mentioned here that the transport rate of permeation has to be high enough to achieve reasonably rapid separation. A good mechanical and chemical stability of these membranes is important. There are different types of membranes available which are as follows: microporous membranes, homogeneous membranes, charged membranes, and thin membranes. There are numerous applications of these membranes. Some of these are listed below: ultrafiltration, reverse osmosis, dialysis, and electrodialysis. Unit 11 of Block 5 of this course is assigned for the detailed discussion on membrane separations. Gel filtration has taken the form of a regular chromatography. This is also known as gel permeation or size exclusion chromatography. The column packing materials are polymer beads and silica-based particles containing a network of uniform pores into which the solute and solvent molecules can diffuse. In a column operation, the solute molecules which are small enough to enter the pores of gel are retarded, while the molecules large enough not to enter the pores will spend all their time in the mobile phase and move rapidly through the column. This is a useful technique for the separation of high molecular weight natural products from low molecular weight species and salts. It is also used for the rapid determination of molecular weight. The separation by gel permeation can be carried out at high pressure with an HPLC instrument. The details of this branch of chromatography are given in Unit 10. 1.6.7 Electromigration. The simplest example of separation by migration under electric field is controlled potential electrodeposition. This method is quite effective for the separation of certain metal ions in the presence of other metal ions. But in the normal classification of separation methods, it is not given its due recognition. However, the techniques like electrophoresis and electrochromatography, in which an electric field is utilized to produce or affect the relative motion of charged species in solution, have gained more prominence. The two frontline techniques included under this head are electrophoresis and electrochromatography. In electrophoresis, only the electric field causes the motion, while in electrochromatography, the movement is caused by the resultant of an electric and a gravitational or other non-electrical forces. Electrophoretic separations are performed in two different ways. One is called slab electrophoresis and the other capillary electrophoresis. In slab electrophoresis, a filter paper, porous glass or a gel cast in the form of a bed can be used. Samples are introduced as spots or band and a DC potential is applied across the slab for a fixed period. The separated species are visualized by staining in a way similar to TLC. In capillary electrophoresis, a buffer-filled capillary tube is used. The tube extends between two buffer reservoirs that also holds the platinum electrodes. The sample is introduced at one end and a DC potential is applied. The separated analytes are observed by a detector at the other end. The simplest form of electrochromatography is by fusion of electrophoresis and paper chromatography. The sheet of paper is usually suspended vertically with a solvent, buffer, descending from the top. The electric field is applied horizontally along the sides of paper. The capillary electrochromatography is a more sophisticated version of the paper electrochromatography. It is a hybrid of capillary electrophoresis and HPLC and offers some of the advantages of the two techniques. The different aspects of separation by electromigration are discussed in Unit 12, 1.7 classification based on equilibrium and rate processes. Now we have seen that the different types of separation methods have been classified under various categories based on property resulting into separation. Practically, all these methods can be divided into various classes using equilibrium and rate processes as criteria. The equilibrium processes are based on differences in the properties of individual components. These processes are generally based on phase equilibria and involve the distribution of substances between two phases. Rate processes are based on the kinetic properties of the components. It is already clear that a majority of important separation processes are chromatography based, therefore, it may be reasonable to introduce a subclassification of the method listed under this head as chromatographic and non-chromatographic methods. 1.7.1 Classification based on equilibrium processes. It has been pointed out in the preceding section that in equilibrium processes there are two competing phases and they could be as follows: gas-liquid, gas-solid, liquid-liquid, liquid-solid, gas-liquid. Some of the important methods in which gas and liquid are the two phases involved are as follows. 1. Non-chromatographic methods. I. Distillation. E. Foam fractionation. When we say distillation, it means distillation in all its forms. The well-known example of foam fractionation is concentration of ores by froth flotation process. 2. Chromatographic method. I. Gas-liquid chromatography. B. Gas-solid. When the two phases are gas and solid, a few examples of the methods are as given below. 1. Non-chromatographic methods. I. Sublimation. E. Adsorption. 2. Chromatographic methods. I. Gas-solid chromatography. E. Exclusion chromatography. In the case of sublimation, the solid is directly vaporized and the equilibrium exists between the gas and the solid. Adsorption of gases by solids is a well-known method of separation and this forms the basis of gas-solid chromatography. Exclusion of molecules based on shape and size of both gas and liquid can take place. See, liquid-liquid. In this case, two immiscible liquids come in contact with each other. Here, the separation takes place because of favorable partition of one or more components in one of the phases. 1. Non-chromatographic method. I. Liquid-liquid extraction. 2. Chromatographic methods. I. Liquid-liquid column chromatography. E. Liquid-liquid planar chromatography. E. High-pressure liquid chromatography. D. Liquid-solid. 1. Non-chromatographic methods. I. Precipitation. E. Fractional crystallization. 2. Chromatographic methods. I. Adsorption chromatography, column and planar. E. Ion exchange chromatography. E. Affinity chromatography. IV. Exclusion, gel permeation, chromatography. 1.7.2 Classification based on rate processes. The separations based on rate processes take place due to differences in the kinetic properties of the components of the mixture. The separations are mainly achieved due to the following two reasons: different diffusion rates through permeable barriers such as membranes, different migration velocities under various fields like electrical, gravitational, and thermal. A. Different diffusion rate through permeable barriers. The most commonly used permeable barrier is semi-equals permeable membrane. The methods based on its use are I. Ultrafiltration, E. Reverse osmosis, E. Dialysis, and IV. Electrodialysis. B. Field separations. Electrical field is commonly used to affect separations, and the different methods which are based on the application of this type of field are I. Electrodeposition, E. Electrophoresis, E. Capillary electrophoresis, and IV. Electrochromatography. The examples for separations resulting due to application of gravitational and thermal fields are ultracentrifugation and thermal diffusion, respectively. After going through both types of classification, one can see that most of the known techniques are included in one or the other category. But it may be mentioned that the list of separation methods considered for classification is not exhaustive. Some of the lesser known methods have not been taken into consideration. The other point which has to be kept in mind is that in some of the methods, particularly chromatographic, more than one mechanism is operative and the method may be classified under different categories. 1.8 Criteria for selection of separation methods. Now we have some idea about a majority of separation methods. The advantages, applications and limitations of some of the important methods will be discussed in the different units of this course. It may be a little premature to make a comparison of the methods, particularly when we do not have sufficient background of the different separation methods. Moreover, the assessment of utility of a method is really a situation-based problem. To elaborate this point, one can cite that the selection of a method will be determined by the physical state of mixture, its complexity, amount of sample available, the speed required, and the level of purity desired. Over and above this, one important point that has to be kept in mind is that whether the method has to be used for analysis or synthesis, recovery, purification. If a method has to be used on an industrial scale, some different considerations also get prominence. In a situation like this, it is a little difficult task to impart special importance to one or the other criteria. However, having known about the utility of the separation methods, we can talk about some of the general criteria for the selection of the separation methods. They are selectivity, detectability, yield, speed and convenience, capability for hyphenation, and ease in scaling up and economics. We will now briefly explain each one of them. 1.8.1 Selectivity. The foremost and most important is the selectivity. The selectivity relates to the capability of the technique to separate the desired component effectively from a complex mixture, particularly containing closely similar components. The term effective separation is expressed in terms of resolution, separation factor, decontamination factor and percentage purity. All these terms, in one form or the other, will appear in different units of this course. 1.8.2 Detectability. The term detectability refers to the minimum amount that can be detected. It is also termed as sensitivity. In the case of detectors, it can be calculated based on certain assumptions such as detection at 2 or 3 times the noise level observed at the baseline. Sensitivity can also be determined practically. Sensitivity can be improved by properly optimizing the separation conditions using the same detector. Sensitivity assumes paramount importance when the quantity of mixture to be analyzed is very small or trace impurities for obtaining an ultra-pure material are to be assayed. 1.8.3 Reproducibility. The method should be such that it gives reproducible results of separation. It is usually expressed in terms of standard deviation or coefficient of variation based on replicate measurements. Now at this point, it may be important to point out that the separation conditions should not be such that a slight variation in the conditions may alter the result significantly. A flexibility in the conditions of separation is always preferred. This is particularly important if the process is to be scaled up on a Commercial scale. 1.8.4 yield, speed and convenience. In all those methods in which a simultaneous quantification of the separated product is done, a quantitative recovery of the separated product is a must. Naturally, a method giving a higher yield is preferred. In cases where the yield is not high, the remaining portion may have to be recycled. Speed of the separation is another critical parameter. Any technique which is AWE fully slow in achieving the separation goes in the background. By properly adjusting the experimental parameters, it is sometimes possible to improve the speed of the separation process. Speed, as a criteria, assumes great significance if the constituents of the mixture degenerate or decay. A typical example is the separation of radionuclides with very short half-lives. In such a situation, speed becomes more important than the yield. Literally, the convenience of a separation method is a very broad term. The method of separation should be such that there may be little preparative chemistry before subjecting the sample to separation. The conditions of separation should not be very stringent to the extent that it may be difficult to keep a control of the conditions. The product should be obtained in such a form that it can be easily put to use without much chemistry. Moreover, the method can be an asset if it is easily put online operation or easily automated. 1.8.5 Capability for hyphenation. In a majority of chromatographic methods, there is a detector which quantifies the effluent coming out of the column. These detectors are not very sensitive. Also, they have a limited capability of identifying the unknowns. It is known that a mass spectrometer is a very powerful universal detector. Therefore, it is being interfaced with some of the chromatographic techniques. A very important example in this regard is interfacing of a gas chromatograph with a mass spectrometer, GCMS. Gas chromatography is an ideal separator, whereas mass spectrometry is excellent for identification. The aim of an interfacing arrangement is to operate both a gas chromatograph and a mass spectrometer without affecting the performance of either instrument. The problem is compatibility. The interface provides the link between the two instruments. On a similar line, gas chromatography is coupled with infrared spectrometry. The techniques like high-performance liquid chromatography and simple liquid chromatography are coupled with a mass spectrometer. The interfacing makes the technique as a powerful analytical tool. Thus, in nutshell, a separation technique is conveniently interfaced with an effective detecting device like mass spectrometer or spectrophotometer. This can be an additional advantage of the technique. There have been serious efforts in this direction, and even the simple techniques like thin layer chromatography has been interfaced with a mass spectrometer. 1.8.6 Ease in scaling up and economics. It has been repeatedly pointed out that one of the main roles of the separations in technology is in the synthesis, recovery and purification of products. Therefore, the separation methods do not remain necessarily confined to the bench scale. The basic data has to be used to scale up the process to plant scale. The method should be such that it can be conveniently scaled up on a commercial scale without much alteration in basic experimental parameters. Once we talk of the use of the method on a commercial scale, the economics of the process figures in. Not only the economics, the environmental considerations assume significant importance. The commercial method of separation should also be environmental friendly. 1.9 Summary. The present unit provides an introduction to the course on separation methods. It highlights the utility of separations in the analysis and recovery of pure products from complex mixtures. The scope of separations extends from the needs of everyday life to complex technological processes. There is hardly any branch of science or technology which has not been a beneficiary of the developments in separation science. Separations encompass different physiochemical principles, and the subject has itself matured to a unified science. Most of the well-known methods of separations fall under the category of chromatographic methods. It is a little difficult task to categorize the variety of separation methods available today. A simpler classification can be made on the basis of property which results into separation. The other approach that can be adopted for classification is based on the physiochemical phenomena responsible for separation. In other words, these Phenomena can be divided under two categories, the equilibrium and the rate. Processes. In equilibrium processes, there have to be two competing phases. However, in rate processes, the constituents move differently through a permeable barrier or show different migration velocities under various fields, mainly electrical. In both the classifications, it has been possible to classify most of the well-known separation methods in one or the other category. But some of the methods are such that they can be put in more than one category. As regards the criteria to be used for the assessment of utility of a separation method, the whole problem is situation-based. This point can be clarified by the fact that the selection or the utility of a method will be determined by the physical state of the mixture, its complexity, amount of sample available, the speed required and the level of purity desired. It has to be kept in mind that whether the method is to be used for analysis or synthesis, recovery. But this only does not necessarily determine the importance of the different criteria cited in the text. Thank you for watching. We will see you in the next video with the next chapter.